Greetings, everyone. Breaking developments regarding interstellar visitor 3IATLAS demand immediate attention. A new rogue object has been discovered moving through our solar system, positioned directly between 3IATLAS and Earth. This object, designated C2025 V1 Borisov, was first observed by Gennady Borisov of Crimea, the same individual who discovered 2I Borisov, the second confirmed interstellar object ever detected. The timing and position of this discovery raise extraordinary questions about what we are witnessing in our cosmic neighborhood. C2025 V1 Borisov presents characteristics that mirror the anomalies we have been tracking with 3IATLAS. Most significantly, it displays no obvious tail. Only 2 observations out of 10 report any tail structure whatsoever. The remaining 8 show merely a coma, that fuzzy cloud of gas and dust surrounding the nucleus. This absence of a prominent tail directly parallels what we observe with 3IATLAS, despite both objects experiencing intense solar radiation. The pattern becomes more intriguing when we examine their relative positions and brightnesses. The new object currently sits closer to the Sun than 3IATLAS itself. Under normal circumstances, proximity to our star should trigger vigorous outgassing, producing a spectacular tail as frozen volatiles sublimate and stream away from the nucleus. Yet Borisov defies this expectation. Its apparent magnitude hovers around 12 to 13, significantly dimmer than 3IATLAS, which registers at magnitude 9.8. That brightness difference matters because 3IATLAS lies much farther from Earth, yet shines considerably brighter. The implications of this disparity deserve careful consideration. 3 celestial objects now cluster together from Earth's perspective. C2025 V1 Borisov moves through the constellation Virgo, nearly conjunct with 3IATLAS. Meanwhile, C2025 K1 Atlas, an entirely separate comet displaying unusual golden coloration, traverses the constellation Leo. All 3 objects appear relatively close together in our night sky, creating a remarkable celestial configuration. This arrangement becomes even more extraordinary when we examine the precise alignment occurring within the next 48 hours. On November 8th, Earth, Borisov, and 3IATLAS will achieve near-perfect alignment. While Borisov sits above the ecliptic plane, the 3 objects will form a straight-line configuration from our planetary perspective. This geometric arrangement carries implications beyond mere coincidence. The alignment occurs just as Borisov approaches its perihelion, the closest point to the Sun in its orbital trajectory. That perihelion passage is calculated for November 16th, placing the object well above the ecliptic plane at roughly Earth's orbital distance from the Sun. Borisov was initially catalogued as GB000810 before receiving its official designation. Researchers conducting their own investigations may find more data under that preliminary identifier. The object emerged from below the ecliptic plane, shooting upward through our solar system. Its trajectory carries it above the plane before swinging back around. This motion pattern, combined with its position between Earth and the interstellar visitor, creates a scenario that astronomers are monitoring with intense interest. The absence of a prominent tail on Borisov mirrors one of the most puzzling aspects of 3IATLAS. Despite passing through perihelion, despite enduring massive solar storms that erupted between October 21st and the perihelion passage, despite intense radiation bombardment, and 3IATLAS has consistently failed to develop the expected tail structure. Comets approaching the Sun should outgas vigorously. They should shed frozen materials that sublime into space, creating those iconic streaming tails that have captivated humanity for millennia. Both objects defy this fundamental expectation. Observatory data from the International Astronomical Union's Minor Planet Electronic Circular reveals the discrepancies in tail observations. 10 separate reports document Borisov's characteristics. 8 report only a coma. The 2 that mention tail structures disagree dramatically on measurements. One observer reports a tail extending 50 arcseconds, while another measures 72 arcseconds. Meanwhile, coma measurements show similar inconsistencies, ranging from 23 to 40 arcseconds. These variations suggest either genuine variability in the object's behavior or significant observational challenges. Either explanation raises important questions. The discoverer himself, Gennady Borisov, detected no tail structure in his initial observations. Given his experience discovering 2I Borisov and his quality equipment, this absence carries weight. Most subsequent observers confirm his assessment. The object presents a coma without obvious tail development. This characteristic becomes particularly striking when we consider Borisov's current proximity to the Sun, closer even than 3IATLAS during its perihelion passage. Solar activity adds another layer of complexity to this situation. A massive sunspot group currently facing Earth has been unleashing powerful solar flares and coronal mass ejections. These eruptions began targeting 3IATLAS on October 21st, when the comet was approaching superior conjunction with the Sun. The bombardment continued through perihelion and beyond. Such intense radiation and particle bombardment should trigger dramatic outgassing from any icy body. Yet 3IATLAS emerged from this assault without developing a prominent tail. The sunspot group's orientation creates alignments with multiple objects. Currently, the active region faces comet A6, Lemon, maintaining a direct line between Earth, the Sun, and Lemon. This geometric configuration may explain the sustained high level of solar activity impacting our planet. As Earth rotates and the Sun's active regions evolve, different objects enter and exit these direct alignment zones. When Borisov reaches perihelion on November 16th, it too will achieve alignment with these same active regions, potentially subjecting it to similar radiation bombardment. 3 distinct objects now populate the inner solar system simultaneously, each displaying unusual characteristics. C 2025K1 Atlas glows golden yellow, an uncommon coloration for comets typically dominated by blue and green emission lines from ionized gases. C 2025 V1 Borisov lacks an obvious tail despite solar proximity. And 3IATLAS, the interstellar visitor, continues defying multiple predictions about its behavior and appearance. The concentration of anomalous objects in this time period and spatial region exceeds normal statistical expectations. China's space agency finally released imagery captured by the Tianwen-1 Mars orbiter. This spacecraft photographed 3IATLAS between October 1st and 4th, observing from its position in Martian orbit. The images show the comet moving against the stellar background, a technical achievement given the challenges involved. Tianwen-1 had to switch from imaging bright planetary surfaces to tracking a faint object moving at 58 kilometers per second from a distance of 28.96 million kilometers. The high-resolution imaging camera successfully captured these observations, clearly showing the nucleus surrounded by its coma. The China National Space Administration described the images as clearly displaying the comet's distinctive features, consisting of a nucleus and surrounding coma with a diameter reaching several thousand kilometers. This coma measurement aligns with other observations, confirming that 3IATLAS maintains a substantial envelope of gas and dust, despite the absence of an obvious tail. The material surrounds the nucleus, but does not stream away in the characteristic tail formation we expect from active comets. However, the image quality disappoints. The resolution appears extremely low, pixelated to the point where detailed analysis becomes difficult. Some observers detect hints of material extending behind the nucleus, possibly indicating minimal tail development. But the image quality makes definitive conclusions impossible. The Chinese Space Agency positioned this observation as an important extension mission for Tianwen-1, providing valuable technical experience for future deep space exploration missions. Yet the scientific return from these specific images remains limited. This release leaves NASA's Mars Reconnaissance Orbiter as the primary hope for high-quality imagery. The MRO carries the HiRISE camera, capable of extraordinary resolution. Multiple reports indicate that HiRISE successfully observed 3IATLAS during its close approach to Mars. Congressional inquiries have been submitted requesting the release of this data. NASA's response attributes the delay to the current government shutdown. Officials state that imagery will be released immediately once normal operations resume. Some analysts suggest the HiRISE images may not differ dramatically from the Chinese observations in terms of what they reveal about 3IATLAS. Both spacecraft observed from similar distances, and both dealt with the fundamental challenge of imaging a relatively small, fast-moving object against the stellar background. However, HiRISE's superior resolution should at minimum provide better constraints on the nucleus size and potentially reveal surface features or composition indicators not visible in the lower resolution Chinese imagery. The brightness of 3IATLAS continues exceeding predictions. Light curve data tracking the comet's apparent magnitude from July through the present shows a consistent pattern of overperformance. Initial observations placed the object below the simple fitted brightness curve. Then, in early September, it began brightening more rapidly than models predicted. This enhanced brightening continued through its passage behind the Sun, as observed by SOHO's coronagraphs and NASA's Punch constellation of spacecraft. The most recent magnitude measurement places 3IATLAS at 9.8, compared to an expected value of 11.2 based on the simple brightness model. Remember that each magnitude step represents a factor of 2.54 in brightness. A difference of 1.4 magnitudes means the comet currently shines roughly 3.5 times brighter than predicted. This excess brightness occurs despite the comet's distance from the Sun increasing as it moves outward along its hyperbolic trajectory. Several factors could explain this brightness anomaly. Increased activity on the comet's surface would produce more gas and dust, reflecting more sunlight. The composition of the nucleus might differ from typical solar system comets, containing more reflective materials or more readily sublimating ices. The geometry of the coma might focus reflected light toward Earth, or the nucleus itself might be larger than initial estimates suggested. Each explanation carries different implications for understanding this interstellar visitor. The non-gravitational acceleration detected in 3IATLAS provides another piece of this puzzle. When a comet outgasses, the escaping material produces a rocket effect, slightly altering the object's trajectory away from the path determined purely by gravitational forces. Astronomers measure these deviations to understand outgassing rates and mass loss. Early calculations suggested 3IATLAS displayed measurable non-gravitational acceleration consistent with active outgassing. However, updated orbital calculations performed on November 5th show less non-gravitational acceleration than initially computed. The acceleration still exists, but appears smaller than earlier models indicated. This revision suggests either that outgassing rates are lower than first thought, or that the earlier measurements contained errors that subsequent observations have corrected. The reduced acceleration makes the absence of an obvious tail even more puzzling. If material is escaping at rates sufficient to alter the orbit, where is the visible tail? Harvard University professor Abraham Loeb has proposed that this non-gravitational acceleration might indicate something other than natural outgassing. Writing on Medium, Loeb calculated that 3IATLAS would need to lose at least 10% of its mass through gas ejection to produce the observed acceleration. Such massive mass loss should create a dense, easily observable cloud of gas around the comet, particularly visible in November and December as the object approaches Earth. Loeb argues that if observations in December fail to show this expected gas cloud, then cometary evaporation cannot explain the non-gravitational acceleration. He suggests this might constitute a technological signature of a propulsion system. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, could potentially observe 3IATLAS in early November and detect evidence of this mass loss. Ground-based telescopes will have optimal viewing opportunities on December 19th when 3IATLAS reaches its closest approach to Earth. Other planetary scientists dispute this interpretation. Darrell Seligman from Michigan State University points out that comets routinely display non-gravitational accelerations. Scientists measure these effects regularly in both short-period and long-period comets. The phenomenon results from the rocket-like recoil produced when gas blows off the comet's surface. These accelerations can be quite subtle and difficult to measure precisely, but they remain a standard feature of cometary behavior. Seligman notes that the first interstellar object, 1I Oumuamua, also exhibited non-gravitational acceleration without displaying an obvious dust coma. Additionally, a class of objects called dark comets exists in the near-Earth environment. These bodies show no apparent tails, but demonstrate comet-like non-gravitational accelerations. The absence of a visible tail does not necessarily indicate anything technological or non-natural about an object's behavior. Megan Schwam from Queen's University, Belfast, emphasizes that peer-reviewed analysis of 3IATLAS data collected from Discovery through its solar approach shows consistency with natural origin. The object's properties align with expectations for an icy planetesimal that formed around another star. Differences in composition, compared to solar system comets, are expected because 3IATLAS formed in a different stellar environment with different chemical abundances. A star with composition different from our Sun would produce a planet-forming disk with correspondingly different properties. Objects forming in that disk would naturally show compositional variations from their solar system counterparts. The debate illustrates a fundamental challenge in interpreting observations of interstellar objects. We have no direct experience with materials formed around other stars. Our entire understanding of cometary composition derives from studying objects born in our solar system. When an interstellar visitor displays unusual properties, we must carefully distinguish between genuine anomalies suggesting exotic origins and expected variations resulting from different formation environments. This distinction requires extensive data and careful analysis. The current roadblocks preventing comprehensive observations of 3IATLAS frustrate the scientific community. The Chinese images, while historically significant as the first observations from another planet, provide limited scientific value. The NASA imagery remains embargoed pending government operational status. Hubble Space Telescope and James Webb Space Telescope observations face scheduling challenges and data release timelines. Ground-based observations continue, but face limitations from the comet's position and brightness. Meanwhile, 3IATLAS continues its journey through our solar system. Each day carries it farther from the Sun and closer to Earth before it eventually swings past our planet and heads back toward interstellar space. The object represents an extraordinary scientific opportunity. Interstellar visitors provide our only current means of directly sampling material from other stellar systems. Every measurement, every spectrum, every image adds to our understanding of conditions beyond our solar neighborhood. The presence of C2025 V1 Borisov between 3IATLAS and Earth adds an unexpected element to this story. Whether Borisov proves to be another interstellar visitor, an unusual solar system comet, or something else entirely, its timing and characteristics merit close attention. The alignment of multiple unusual objects creates a natural experiment, allowing comparative observations under similar conditions. How Borisov responds to increased solar radiation as it approaches perihelion will provide valuable context for interpreting 3IATLAS behavior. Solar activity remains elevated, with geomagnetic storms impacting Earth's magnetosphere. Recent activity reached G3 levels, defined as strong geomagnetic storms producing significant fluctuations in Earth's magnetic field. Predictions suggest continued strong to severe storm conditions over the coming days. The active sunspot groups responsible for these eruptions maintain favorable geometry for Earth-directed emissions. As these regions rotate with the sun's surface, they will eventually direct their output toward the positions of Borisov and other objects in the inner solar system. The correlation between solar activity and celestial alignments presents an intriguing pattern. As different objects achieve geometric alignment with active solar regions, they experience enhanced radiation bombardment. This natural variation in exposure helps explain why some comets develop prominent tails during certain phases of their orbits, while remaining relatively inactive during other phases. The radiation environment varies dramatically depending on solar activity levels and the specific geometry of the comet's position relative to active regions. Observatory networks worldwide continue monitoring all these objects. Professional facilities contribute dedicated observation time. Amateur astronomers with increasingly sophisticated equipment provide valuable supplementary data. The Minor Planet Center collects and disseminates positional measurements. Spectrum analyzers characterize the composition of cometary gases. Photometric studies track brightness variations. This coordinated international effort assembles a comprehensive picture from thousands of individual observations. The scientific process moves forward through the accumulation of data and the iterative refinement of models. Early observations establish basic parameters. Follow-up observations test predictions and reveal unexpected behaviors. Theoretical models attempt to explain the observations. New observations either confirm or challenge those models, leading to revised theories and improved understanding. The interplay between observation, theory, and prediction drives scientific progress. For 3IATLAS specifically, we have now accumulated months of observations across multiple wavelengths and from multiple vantage points. Earth-based telescopes tracked it from discovery through its approach to the Sun. Space-based assets including SOHO, STEREO, and PUNCH monitored it during solar conjunction when Earth-based observations became impossible. The Tianwen-1 orbiter at Mars provided views from a completely different perspective. This multi-platform approach reduces biases inherent in single-viewpoint observations. Future observations will occur under different conditions as the geometry continues evolving. In mid-December, 3IATLAS reaches its closest approach to Earth, providing optimal viewing conditions for ground-based observers. Powerful telescopes will capture high-resolution images and detailed spectra. Radio observations might detect outgassing signatures not visible in optical wavelengths. Infrared observations could reveal thermal properties of the nucleus. Each technique provides unique information contributing to the complete picture. The broader implications extend beyond this single object. The rate at which we detect interstellar visitors helps constrain models of planetary system formation and evolution. Every stellar system likely ejects material during its formation and early evolution. Some of this ejected material escapes into interstellar space, wandering the galaxy until potentially encountering other stellar systems. The frequency of such encounters depends on the total population of ejected objects and the density of stars in the galactic neighborhood. Statistical studies suggest that interstellar objects should pass through the inner solar system perhaps once per year, though most would be too faint to detect. The discovery of 3 confirmed interstellar objects within 8 years indicates our observational capabilities have reached the threshold for routine detection. As survey telescopes become more sensitive and sky coverage improves, detection rates should increase. Within the next decade, we may observe dozens or hundreds of interstellar visitors. Each detection provides constraints on the properties of other stellar systems. Compositional measurements reveal the chemical abundances in distant planet-forming disks. Size distributions indicate the typical outcomes of planetesimal formation processes. Trajectory information hints at the dynamical evolution that ejected these objects from their birth systems. Collectively, These observations build our understanding of planetary system diversity across the galaxy. The current situation with multiple unusual objects transiting the inner solar system simultaneously may simply represent statistical clustering. Random processes naturally produce both droughts and clusters of events. Alternatively, this concentration might indicate a real physical correlation, perhaps related to the Sun's motion through denser regions of the interstellar medium or past disturbances that ejected multiple objects toward our location. Distinguishing between random clustering and physically meaningful correlation requires careful statistical analysis and additional data. Regardless of the explanation, the present moment offers remarkable opportunities for observation and discovery. The combination of improved detection capabilities, multi-platform observational assets, and international coordination enables unprecedented study of these cosmic visitors. We stand in a privileged position to witness and characterize material from beyond our solar system, material that carries information about stellar environments we cannot yet directly observe. The story continues developing. Borisov approaches perihelion. 3I.ATLAS moves closer to Earth. Solar activity fluctuates. Observatories worldwide maintain their watch. Each night brings new images, new measurements, new insights. The scientific community analyzes incoming data, debates interpretations, and refines models. This process exemplifies science at its best, the collective effort to understand phenomena that challenge our expectations and expand our knowledge of the cosmos. Thank you for your attention to these extraordinary developments. The next several weeks promise continued revelations as these objects move through critical phases of their trajectories. Please subscribe, share, and engage with this ongoing story as we track these visitors through our cosmic neighborhood.